Hey guys, welcome to Learn Today IGCSE. In this video, we'll go through all Chapter 4 Electricity and Magnetism questions from the 2024 IGCSE exams including February, March, May, June, and October, November, covering all three variants. Let's get started. The first question is from February, March 2024, Paper 4 Variant 2. Draw the circuit symbol for a potential divider. Make sure you're familiar with all the symbols for electric circuits. If you're not, you can take a screenshot of the screen right now. This is the circuit symbol of a potential divider. Next, question B. Figure 7.1 shows a circuit. Over here, you've got the EMF, which is 6 voltage. You've got a fixed resistor here, and this is a variable resistor. The difference between a variable resistor and a fixed resistor is that for a variable resistor, you can adjust the resistance to control the amount of current flow in the circuit. Question part 1. Calculate the value of V out when the value of R is 3 kilo ohms. So you're looking to find the voltage out when R equals to 3 kilo ohms. What you see here is two resistors that are being used as a potential divider. Most students find it difficult attempting questions on potential divider. However, the concept is actually pretty simple. Let's say I have a voltage in or the voltage supply of 9 voltage. And according to my resistor, if I have 2 ohms here and I have 1 ohm here, I am looking to divide my voltage to each of these resistors accordingly based on its ratio. So the ratio here is 2 to 1. So the voltage out here would be 6 voltage and the voltage out here would be 3 voltage. So you just need to split the voltage according to its ratio. So now let's look at this question. You've got 6 voltage here as your V in. One of the resistor is 1 kilo ohm and the other resistor is 3 kilo ohm. So the voltage is 1 to 3. So if I follow mathematical formula, this is how I'm going to do it. V out would be 1.5 voltage and the other output would be 4.5 voltage. Or another way of solving this is by using the formula. The V in is our supply. So we're going to substitute 6 voltage over here. So R1 here would be the one which is parallel to V out over here. So the value is 1 kilo ohms over the total resistance of both the resistor, 1 plus 3. So rearranging this formula, I would get 1 over 4 times by 6 voltage, which is 1.5 voltage, the same value as here. Part 2. The value of R is adjusted until the current in the circuit is 1.7 milliamperes. Calculate the charge that flows through the circuit in 300 seconds. Whenever you are given with question to calculate, please list down all the information that you have in the question. You have the current and time and you're looking to find charge. There is a formula related to this which is Q equals to I times T. This is pretty straightforward. We're just going to substitute the value into our formula. When using this formula, you have to make sure that your current is in the standard unit of ampere. And right now, it is milliampere. So we have to convert this. Milli is times 10 to the power of negative 3. So just put these values in your calculator and in two significant figures, your final answer would be 0.51 and the unit for charge is coulomb, capital C. Next, question 8 part 1. Figure 8.1 shows a wire carrying a large current. So as you can see here, the flow of current is going into the square card. Part 1. Figure 8.2 shows the square card viewed from above. The cross here is the image of the current entering in the card. When the current flows in, this is the symbol. And when the current is flowing out, you would see a dot. So on figure 8.2, draw 3 magnetic field lines that indicate the direction of the magnetic field and how its strength varies with distance from the wire. Okay, so let's look back at this diagram. To answer this, we need to use our right hand grip rule. When applying the right hand grip rule, the thumb will point at the direction of the current, and the curvature of the grip indicates the direction of the magnetic field. In this case, the current is pointing downwards, so your thumb should also be pointing downwards, like this. And you will notice that the curvature of your grip is this direction, meaning that the magnetic field will also be in this direction, which is clockwise. Okay, so now we're going to draw 3 circles in a clockwise direction. You also have to show how its strength varies with distance from the wire. To do this, we have to understand how current affects the magnetic field. The magnetic field is stronger when it is closer to the current, and as it moves further, the strength of the magnetic field will decrease. We can demonstrate the strength of a magnetic field by drawing the magnetic field lines closer to each other. And to demonstrate a weaker magnetic field, we will draw the magnetic field lines further from each other. So that's what we're going to do over here. As it moves further from the current, the magnetic field in this region would be weaker. Draw the lines further as it moves away from the current. Next, part 2. The current in the wire increases and the direction of the current is reversed. State how these changes affect the magnetic field. If I increase the current as mentioned, my magnetic field will also increase, meaning that the magnetic field lines will now be closer to each other. And as for the direction, if I change the current direction moving upwards, then now my thumb will be pointing upwards like this, and my curvature grip will be in anti-clockwise direction. So the magnetic field line will go on the opposite direction. So those are the changes that would affect the magnetic field. Question B. Electricity is transmitted at high voltage. Explain why a high voltage increases the efficiency of transmission even with thinner wires. Thinner wires have smaller cross-sectional area, meaning that it will have a higher resistance. And according to the formula of P equals to I times V, we know that if the voltage increases, the current must decrease for the same power. And we can use the formula of P equals to I squared times R to calculate power loss as heat energy. Therefore, reducing the current dramatically can reduce the power loss in the cables. The next question is from May June 2024, Paper 4, Variant 1. Figure 6.1 shows an isolated metal sphere suspended by an insulating thread from the ceiling. This is the insulating thread and this is a metal sphere. This experiment is the charging of conductors by induction. And the other experiment you have to know is the charging of insulators by rubbing. These two are in your syllabus, so make sure you are familiar with it. Moving on, the sphere is negatively charged. Question part A. The charge on the sphere produces an electric field in the surroundings. Part 1. State what is meant by electric field. If you're unfamiliar with the definitions, you can always refer to your syllabus course specification. So under 4.2, it has been given to you that electric field is the region in which an electric charge experiences a force. Remember that all definitions can be obtained by your syllabus course specification, so make sure you go through them and memorize what is necessary. Next, question part 2 on figure 6.1. Show the pattern and direction of the electric field produced by the charge on the sphere. You are required to draw at least 4 lines. Remember that the electric field for negative charge is inward, whereas for positive charge is outward. Think of it in a way that you always want to spread positivity, so for positive it moves outward. Make sure the lines are touching the sphere and there is an arrowhead moving inwards. Next, question B. The magnitude of the charge on the sphere is 3.5 times 10 to the power of negative 10 coulomb. An earthed metal wire is touched against the surface of the sphere and the sphere is discharged. Part 1. State what happens in the wire as the sphere is discharged. Okay. Remember that if any earthed wire or ground wire is attached, then the electrons will move through the wire into the earth. So since the question is just asking you what happens in the wire, you can just mention that the electrons will flow in the wire from the sphere into the earth. Next, part 2. It takes 0.1 nanoseconds for the sphere to discharge completely. Calculate the average current in the earthed wire as the sphere discharges. So pay attention here that the unit here is in nanoseconds. Nano is times 10 to the power of negative 9. So 0.14 times 10 to the power of negative 9 seconds is the time taken. You are asked to find for the current, and another information that was given to you is the charge. So the formula related to this is Q equals to I times T. Rearranging current as your subject, you would get I equals to Q over T. Now just substitute your values in. Current of 2.5. And do not forget your unit for current is ampere. If you're finding this useful, check out my website where I've compiled IGCSE exam questions by topic from 2020 to 2024. The link is provided in the description box below, or you can just click on learntoday.igcse.com. On the website, you will see all the revision courses and click on physics topical questions, and you get to see a preview down here. Once you're ready, add it to your cart and proceed to check out. Just enter your name for billing purposes. Don't worry about the address, you can just use the sample one provided in the video. Since this is a PDF ebook, nothing will be shipped to you. Once the payment is complete, you'll be able to download your copy immediately. Next, question 7. The electromotive force of a battery is 7.5 voltage. Define the term electromotive force. Again, you are asked for definition. Make sure to go through your syllabus. Electromotive can be defined as the electrical work done by a source in moving a unit charge around a complete circuit. Make sure to memorize your definition, as there are quite a number of questions that test you on this. Next, question B. The battery is connected in series with a variable resistor and a 30 ohms resistor. The battery is made using a 1.5 volt cells. Part 1. Draw a circuit diagram that shows all the 1.5 cells connected to produce an EMF of 7.5 voltage, the variable resistor and the 30 ohm resistor. So you have a total EMF of 7.5 voltage and you are only given with a 1.5 volt cells. So this means that we are required to draw a total of 5 cells to make up 7.5 voltage. And make sure to draw your variable resistor, this is the symbol for it, and a fixed resistor, this is the symbol for it. Next, part 2. The resistance of the variable resistor can be varied from 0 ohm to a maximum resistance of 150 ohms. Using the axis in figure 7.1, draw a graph to show how the current in the circuit varies with the resistance of the variable resistor as it increases from 0 ohm to 150 ohm. Okay, before that, we first need to understand the relationship of current and resistance. According to Ohm's law, the relationship of current and resistance is inversely proportional. Since the value of EMF is fixed, as the value of current increases, the value of resistance will decrease, and vice versa. If the value of resistance increases, the value of current decreases. Therefore, your graph would roughly look like this. This is how an inversely proportional relationship should look like. You are asked to determine and label the value of the maximum current on the y-axis. So to get a maximum current, you must have the lowest resistance. So let's see. We've got a 30 ohm resistor, and since the variable resistor can vary from 0 to 150, let's start with the lowest. Since this is a series circuit, you just have to add your resistance, giving you a total of 30 ohms. Now, according to Ohm's law, if we rearrange current as the subject, it will be voltage over resistance. So the total voltage was 7.5 ohms, and the lowest resistance that we calculated so far is 30 ohms, giving you a maximum current of 0.25 amperes. So when the variable resistor is 0, like this, we will get a maximum current of 0.25 amperes. Now let's see when the variable resistor is at 75 ohms. Then the total resistance of the circuit would be 105 ohms, giving you the current of 0.071. Half of the axis will be 0.125 and 0.071 should be somewhere around here. And when the variable resistance is at its maximum of 150 ohms, then the total resistance of this circuit is 180 ohms, with the value of current at 0.042, somewhat around this point. So as you can see, it fits the pattern of an inversely proportional graph that looks like this. Question 7, Part A. Figure 7.1 shows 3 bars of steel A, B, and C. A student is given the 3 pieces of steel. 2 of the pieces are magnetized and 1 piece is unmagnetized. Describe and explain how the student determines which piece is unmagnetized using only the 3 pieces of steel. Alright, let's assume that the first 2 bars of the steel are magnetized, meaning that they have north and south pole. However, the 3rd bar of steel is unmagnetized. So what we're going to do is take one of the bar of the magnet and place it next to the other bar and check to see if it attracts each other. Now reverse the bar magnet and see what happens. If it repels, this tells us that it is magnetized. Now we're going to repeat the same thing for the other bar of steel. Place it next to each other and we'll observe what happened. We'll reverse the pole and see what happens again. If it attracts even though we have reversed the bar magnet, which tells us that it does not have any north or south pole. Next question B. Figure 7.2 shows a circuit diagram of a step-down transformer. Now, the role of a transformer is to change the size of the alternating voltage. For instance, the voltage in is at the primary coil and the voltage out is at the secondary coil. If you have more number of turns in your primary coil and smaller number of turns in your secondary coil, it is called a step-down transformer, whereby you are reducing the size of the output voltage. Question part 1. The mains voltage supplied to the transformer is 240 voltage. So supplied here being the primary voltage or the voltage input. The output power of the transformer is 45 watts. The transformer is 100% efficient. 100% efficiency means that the power in is equal to the power out. Calculate the input current to the transformer. So we are looking to find the current at the primary coil. The formula related to this would be input power equal to output power, whereby the voltage and current of the primary coil is equal to the voltage and current of the secondary coil. We already know that the power out is 45 voltage, so we're just going to write 45 watts. Sorry, not voltage. The voltage in the primary coil is 240 and we're looking to find the current. So the current that we will obtain is 0.19 amperes. Next, question part 2. Draw a labeled diagram of a step-down transformer. On the label, state a suitable material for each of the components. So a step-down transformer means that you will have a more number of coil at the primary and lesser number of coil in the secondary. And this is how it should look like. However, we will not get a complete 3 marks if we do like this because you are asked to also label the diagram. The material used would be soft iron core. The coils would be made of copper. And lastly, don't forget to label the primary coil and the secondary coil. Next, question 8, part A. Figure 8.1 shows a circuit. The circuit is designed to switch on a night light when the surroundings are dark. Alright, so let's first identify all the components that you can see in your circuit. We have here a power supply, a fixed resistor, a light-depending resistor, and a light-emitting diode. Remember that a light-dependent resistor changes its resistance depending on the surrounding light. If there is more light, its resistance will be low. If there is less light, its resistance will be high. However, a light-emitting diode is going to produce light. LDR receive light and LED produce light. So it's not the same thing and make sure you know the differences. Question part 1. On figure 8.1, draw the circuit symbol for a voltmeter used to measure the potential difference across the light-dependent resistor. So this here is your light-dependent resistor. A voltmeter has to be placed opposite of your component. So you can place it like this or even opposite on the other side like this. It doesn't matter as long as it is on the opposite side and not along the lines of the circuit. Next question part 2. The surroundings changes from light to dark. State the effect of this change on the resistance of the LDR. When there is low light which is dark, the resistance increases. Next part 2. State and explain the effect of this change on the potential difference across the light emitting diode LED. So we need to find out what happens to the potential difference across the diode. So if the voltage travels in this direction, when it reaches this junction, the voltage will remain constant. However, when the light decreases, the resistance of this has increased. So let's say initially it was 10 ohm, now it increases to become 20 ohm. We will notice that the overall resistance of the circuit has increased. So if the resistance increases, the potential difference will also increase. Next question part B. Figure 8.2 shows another circuit. Lamps A and lamps B are identical filament lamps. If they mention to you that it's identical, remember that they are trying to tell you the resistance are the same. The current supplied by the power supply is 0.5 amperes. Calculate the resistance of lamp A. So we are looking to find the value of R for lamp A. We are given with the voltage and we are given with the current, which means that we can apply Ohm's law, whereby voltage equals to current times resistance. If we rearrange this equation, we will get resistance equal to voltage over current. So let's find out what is the voltage received for lamp A and what is the current that goes through lamp A so that we can get the resistance across lamp A. The rule for a parallel circuit is that the voltage is equal everywhere. So lamp A is going to receive 240 voltage. Now let's look at the current. The current travels, it receives 0.5 amperes, and when it reaches this junction, again we've got a parallel circuit. However, the rule of current in a parallel circuit is that it will split. Since it is an identical filament lamp, it will split equally. So 0.25 and 0.25, and then join back together and it becomes 0.5. So the current received for lamp A is 0.25 ampere. So just put this value in your calculator and you will get 960. Do not forget your units, ohm. The next question is from May-June 2024, Paper 4, Variant 3. Question 7. Figure 7.1 shows two charged metal plates. X marks the position of the center of the space between the plates. This is a positively charged plate and at the bottom is the negatively charged plate. Question A, Part 1. On Figure 7.1, draw at least 4 field lines to show the pattern and the direction of the electric field between the two charged plates. Positive particles always have an outward field lines, whereas negative particle will have inward field lines. So this is what it's going to look like from positive going outwards and inwards into the negative plate. Alright, question part 2. Describe the effect on a negatively charged particle placed at X. So if you place a negative charged particle in the center like this, it will be attracted to the positively charged plate and repelled from the negatively charged plate. Next question, part B. During a thunderstorm, an electric field is set up between a cloud and the ground. Charges on the cloud and on the ground are shown in Figure 7.2. The lightning shown in Figure 7.2 discharges a current of 28,000 ampere for 0.0012 seconds. Calculate the charge that flows from the cloud to the ground. So we have the current and time given to us and we are looking for charge. The formula related to this is charge equals to current times time. Since the current is in the standard unit of amperes and time is in second, we can just multiply them together, giving us a value of 34 and the unit for charge is coulomb. Next, part 2. The lightning transfers 1.2 times 10 to the power of 8 joules of energy. Calculate the potential difference between the base of the cloud and the ground. So we are given with energy, current, time, and we are looking to find the voltage. The formula related to this is energy equals to power times time. And power can be calculated by current times voltage. Since we are looking for voltage, we can make it as the subject. Everything is in the standard unit, so we can just substitute them, giving us a voltage of 3.6 times 10 to the power of 6, and the unit for potential difference is voltage. Next, question 9. Figure 9.1 shows a mobile phone being charged on the wireless charging plate. We've got a primary coil and then a secondary coil in the mobile phone. Question A. When the charging plate is switched on, there is an alternating current in the primary coil. A secondary coil is in the mobile phone. Explain how a current is produced in the secondary coil. So you can use the principle of how a transformer works to explain how the current is generated in the secondary coil. For the first point, you could mention that the alternating current in the primary coil will produce a changing in magnetic field. Therefore, the secondary coil now cuts this magnetic field, which induces the current in secondary coil. Next, question B. The maximum energy stored in the battery on the mobile phone is 0.012 kilowatt-hour. Part 1 shows that this maximum energy is 4.3 times 10 to the power of 4 joules. Okay, so this can be proved easily as long as you understand that 1 watt is equal to 1 joules per second. So meaning that 1 watt measures the rate of energy transferred. So what's going to happen here is just a unit conversion. We're going to change kilowatt hour into joules per second. So first thing we're going to do is change 0.012 kilowatt hour into watts. And that can be done by multiplying 1000, giving you 12 watts hour. And since this is joules per 1 second, we're going to change the hour into seconds by multiplying 60 minutes and then with another 60 seconds, which then will give you 43,200. Converting this into standard form, 1, 2, 3, and 4, is going to give us 4.3 times 10 to the power of 4 joules. So this is how you prove it. Next is question part 2. The charging plate in figure 9.1 has a useful output power of 15 watts. The phone manufacturer claims that the battery can be charged to 50% capacity in less than 30 minutes. Show that this claim is true. So let's first list down the information that we have. We know that the maximum energy transferred is 4.3 times 10 to the power of 4 joules. So let's find out what is the energy that can be transferred in 30 minutes. The formula for energy would be power times time. So the power is already been given to us, which is 15 watts, and the time here is 30 minutes. But don't forget to convert this into seconds, so we're going to multiply it by 60 seconds, giving us a value of 27,000 joules. So this is the amount of energy which is being transferred in 30 minutes. And we know that the maximum power is 4.3 times 10 to the power of 4 joule. So let's find out how many percentage is 27,000 joule out of 43,000 joule, which is 62.79%. So this is more than 50%. So this means that yes, you can supply more than 50% in less than 30 minutes. Question 6. A potential divider is made by connecting a light-dependent resistor and a thermistor in series. Figure 6.1 shows the potential divider, a voltmeter, and a direct current DC power supply connected into a circuit. The voltmeter measures the potential difference across the LDR. So this is the LDR, this is the thermistor, and a voltmeter placed across the component. Question 8. Define potential difference. As for the definition, you can easily find them in your syllabus. Under Chapter 4, you would see that potential difference is defined as the work done by a unit charge passing through a component. Question B. The electromotive force EMF of the supply is E. So they're just telling us that the value of the EMF here is E, which is an unknown value. And describe how the potential difference across the thermistor can be determined using the reading on the voltmeter. Now you have to know that for a series circuit, the current that flows across the circuit is always going to be the same. Whereas for voltage, it will split. For instance, if the power supply was 10 voltage, and if you've got two components of the same resistance, the current will split equally of 5 voltage for each of them. And as for parallel, it would be the opposite of a series circuit. So in order to find the voltage of the thermistor, we're going to take the total voltage, which is E, and we're going to take away or minus the voltage of the LDR in order to get the voltage of the thermistor. So E take away the voltmeter reading of LDR will give us the potential difference across the thermistor. Next, question C. The resistance of the LDR decreases and the resistance of the thermistor increases. Part 1. State what has happened to the light intensity on the LDR and the temperature of the thermistor. Alright, in your syllabus, you will come across 4 types of resistor. A fixed resistor, variable resistor, a thermistor, and light-dependent resistor. A standard resistor have a fixed resistance, and variable resistors can have their resistance changed. Next, a thermistor is technically a variable resistor, but it changes according to heat. When the temperature increases, its resistance decreases. When its temperature decreases, its resistance increases. And lastly, we've got a light-depending resistance, which is also a variable resistor, but it changes according to light. When light intensity increases, the resistance decreases, and vice versa. Now remember that light-dependent resistor receives light and not emit light. So if the resistance of the LDR has decreased, this means that the light intensity has increased. And if the resistance of the thermistor has increased, this means that the temperature has decreased. Next question, part 2. Explain what happens to the reading on the voltmeter. So the resistance of the LDR decreases and the resistance of the thermistor increases. According to the formula of potential divider, if the resistance has decreased, then it will have a smaller proportion of the total resistance, which then will be a smaller proportion of the EMF. Next, question 7. A solid bar is inside a copper solenoid. Figure 7.1 shows that the copper solenoid is connected in series with the battery and a variable resistor. The device shown in figure 7.1 is an electromagnet. Remember that a simple electromagnet is made by coiling wire around a soft metal core. Question A suggests a suitable material for the bar. A suitable material would be a soft iron, as it is a temporary magnet and it can lose magnetism easily. Next question. The right-hand end of the bar is the south pole. Figure 7.2 shows the bar viewed from above. On figure 7.2, draw at least 6 field lines to show the pattern and direction of the magnetic field surrounding the bar. Remember that magnetic field line always travels out of the north pole and enters the south pole. So these are what your 6 lines should look like. Remember that you should not have any lines that overlap each other. Next, part 2, the resistance of the variable resistor increases. Explain what happens to the magnetic field surrounding the bar and state how the pattern of field lines that represent the field changes. According to Ohm's law, resistance and current are inversely proportional. It means that if resistance increases, then your current will decrease. And the flow of current can affect the magnetic field strength. The lower the current, the lower the magnetic field strength. Now we're going to have to state how the pattern of field lines that represent the field changes. If the magnetic field strength decreases, then we can show it in a way that the field lines will tend to get further away from each other. If they are closer to each other, it means that they have a very strong magnetic field. So you can say that as for the pattern, the field lines will appear further from each other. Next, question C. A square coil of many turns is placed close to the bar. Figure 7.3 shows the plane of the square coil, this one, parallel to the flat circular surface at the right hand of the bar. Okay. And the resistance of the variable resistor is alternately increased and decreased. Explain what happens in the wires of the square coil. As discussed previously, if the resistance increases, then your current will decrease. And if the resistance decreases, then your current will increase. The higher the current, the higher its magnetic field. The lower the current, the lower its magnetic field. So this means that if we are changing the resistance, we will be changing the current flow through the solenoid. And if the current flow through the solenoid changes, then the magnetic field changes as well. So if the magnetic field in the copper solenoid changes, then the square coil that is being placed near the solenoid will experience a changing magnetic flux. And this changing magnetic flux will now induce electromotive force in the square coil. This induced EMF is what drives a current in the square coil, if this forms a closed circuit. So as what happens in the wires, we can just mention that the square coil will experience a changing in magnetic flux which then induces electromotive force. Next, question 7. A washing machine has an electric motor and electric heater. This is the motor and this is the heater. And this is the ammeter to measure the current. Figure 7.1 shows a simplified circuit diagram for the washing machine. The heater has a resistance of 25 ohm and the power supply has an electromotive force of 230 voltage. Question part A. State the meaning of electromotive force. Any definition can be obtained in your syllabus. It has been mentioned here that EMF can be defined as the electrical work done by a source in moving a unit charge around a complete circuit. Next, question B. State the potential difference across the heater. So we are looking to find the potential difference, which is the value of the voltage across this heater. The type of circuit that we have here is a parallel circuit. You must know that current, when flowing in a parallel circuit, let's say it's 5 ampere here, it will split to 2.5 and 2.5 ampere if the resistance of the components are equal. However, potential difference, if the electromotive force is 230 voltage, then it will be the same throughout the entire circuit. And for series circuit, it's the opposite. So since this is a parallel circuit and the EMF is 230 voltage, then the heater will also receive 230 voltage. Next, calculate the current in the heater. So the heater has a potential difference of 230 voltage and a resistance of 25 ohm. We can use Ohm's law, which is voltage equals to current times resistance, to find the current, which is 9.2, and the units are ampere. Please do not forget your units in your final answer. Next, question D. The current in the motor is 1.6 amperes. Determine the reading on the ammeter in figure 7.1 and explain your answer. Okay. So the current flowing through the motor is 1.6 ampere and the current flowing through the heater as we obtained previously is 9.2 ampere. The rule states that in a parallel circuit, the current will split. This means that at this junction, the current has split to 9.2 ohms into this line and another 1.6 ampere to this line. So if they flow here and then this comes back to this junction, both their current would combine and flow through the ammeter. So the current that is flowing through the ammeter would be 9.2 amperes adding with 1.6 ampere. So the reading of the ammeter would be 10.8 ampere and this is your explanation. Next, question 9. Figure 9.1 shows a wireless charging plate used to charge the battery in a mobile phone. The coil of wire is a part of an electric circuit. So these are the coil of wire. The charging plate is connected to an AC power supply. AC power supply means the current will flow in both directions. It can go in this direction and also flow in this direction. And the power supply is turned on. Question A. Describe the magnetic field around the charging plate in terms of magnitude and direction. Okay, remember that current influences magnetic field. The higher the current, the higher the magnetic field. The lower the current, the lower the magnetic field. And if the direction of the current is changing, so will the direction of the magnetic field. So we can say that the magnetic field around the charging plate constantly changes since the current is constantly changing. As for the direction, according to your right-hand Fleming rule, the direction of magnetic field is perpendicular to the direction of current. So as the flow of current changes, so will the magnetic field. Question B. A mobile phone is placed on the charging plate as shown in figure 9.2. The coil in the mobile phone is a part of a separate circuit that charges the battery. So this is a secondary coil and it comes separately of a separate circuit. The coil in the charging plate, which is this one, and the coil in the mobile phone, which is this one, they act like a transformer. So transformer usually have a primary coil and secondary coil. Question part 1. Explain why there is a current in the secondary coil shown in figure 9.2. So the principle is the same as a transformer. Make sure you are familiar with the principle of transformer. Here is a 4-mark explanation on the operation of a step-down transformer. You can use the same explanation for step-up as well. It's just that the difference of step-up is that the primary coil is lesser than the secondary coil. So you can take a screenshot or copy these for future references. Back to part 2, suggest why the transformer made from charging plate and mobile phone is not 100% efficient. Whenever asked about efficiency, I would always suggest you guys to talk about losing the energy to the surrounding through thermal energy lost. Next, question part C. The mobile phone battery can be recharged using the charging plate and stores 4.5 times 10 to the power of 4 joules of energy. The current in the secondary coil is 0.63 amperes when the output voltage is 12. Calculate the time taken to fully recharge completely an uncharged battery. So we are looking to find time. The formula related to voltage, energy, current, and time is energy equals to voltage times current times time. Remember that physics is largely calculation based, so be sure that you have memorized every formula in the syllabus. I've made a video on this, so make sure you check it out and memorize them. And make sure that your units are all in standard units. Rearranging this, we will get 6,000 and the unit for time is seconds. Next, calculate the charge passing through the battery in 60 seconds. So the formula for charge is current times time. We already have current, which is 0.63, and the time is 60 seconds. The charge will be 38 and the unit for charge is coulomb, which is capital C. Now the last question is from October-November 2024, Paper 4, Variant 3. Question 5. Figure 5.1 shows a metal sphere S. The sphere has been charged with a negative charge. Question A, Part 1. There is an electric field around sphere S. On Figure 5.1, draw 4 field lines to show the pattern of the field and indicate the direction of the field with arrows on the lines. Remember that you always want to spread positivity, so the way of remembering it is that positive move outwards. And for the negative charge, the electric field move inwards. So use arrowhead to indicate your direction. Next, Part 2. Figure 5.2 shows a position X next to the sphere S. A small negatively charged particle is placed at position X. State the direction of the force on the negatively charged particle at X due to the electric field around sphere S. So we've got two alike charges which are negative, and we know that alike charges will repel each other. So the force of this particle would be towards the left, which is being repelled by S. Next, Part 3. The negatively charged particle at X is released from rest, meaning that the initial velocity is at 0 meters per second. Describe the motion of the small negatively charged particle due to the electric field around sphere S. So let's see what's happening. Initially, the speed was at 0 meters per second, and due to the repulsion force, the particle will move towards the left side, and now it will have a certain amount of speed. So we can understand that the speed has increased. So increasing speed means that the negative particle has gone through acceleration. So we can mention that the particle X will accelerate towards the left side, and the reason being its repulsion force acting on it. Next, question B. Figure 5.3 shows sphere S being spray painted. Sphere S is negatively charged. As the paint particles exit the white nozzle of the paint sprayer, they become charged with a positive charge. Part 1. Explain why the paint particles spread out when they leave the nozzle. All the charges are positively charged. So what's going to happen is they're going to repel each other. As they repel each other, they're going to move further away from each other. Hence why they start to spread out. Next question, Part 2. The sphere can be painted by hand using a paintbrush. Suggest and explain one advantage to using charged paint from a spray gun to paint sphere S. Well, since the paint is positively charged and the sphere is negatively charged, we can say that the positively charged paint particles are now going to be attracted by the negative sphere. And this way, the surface of the sphere can be coated evenly. Next, question 6, Part A. A car windscreen is covered in condensation. Thermal energy is used to remove the droplets of water. The thermal energy is provided by 3 resistors on the windscreen. Figure 6.1 shows 2 possible circuits for the 3 resistors. The 3 resistors are identical. So let's look at the first diagram. So the first diagram here is in a series circuit as everything is connected one way. And the second diagram here, we've got a junction that splits in 2 directions. So this will make a parallel circuit. Question Part 1. Describe 2 advantages of using circuit B. All components in the circuit will receive the same amount of voltage. And the other advantage is that if one component fails to function, the flow of the circuit is not broken, as the other components can still receive current. Describe, in terms of the water particles, the process by which the water droplets are removed from the car windscreen using the heater. So this is your windscreen and the water particles are on the windscreen. So due to the thermal energy radiating on the windscreen, it will transfer the heat to the surface of the windscreen, which causes the water particles to absorb this heat energy, and as it absorbs heat energy, it will have higher amount of kinetic energy, causing it to escape from the surface. And this process here is evaporation. Next, question B. Figure 6.2 shows a circuit containing 2 resistors, P and Q. The circuit is powered by a 12 voltage battery. Calculate the current in resistor Q. Now please memorize this rule. In parallel circuit, the current flow will split according to its resistance. However, the amount of voltage will remain same throughout the entire circuit. So that means resistor Q will receive 12 voltage. So to calculate the current, we can use Ohm's law. Rearranging this, we will get V over R, giving us a current of 0.17, and the unit for current is ampere. Please do not forget your units. Next, calculate the energy transferred electrically when the current labeled in B part 1, which is this, is present in the resistor Q for 5 minutes. The formula we're going to use is energy equals to voltage times current times time. However, the time has to be converted into seconds, so you have to multiply 5 minutes by 60. In two significant figures, we will get an energy of 620 and the unit is joules. Next, part 3. Energy is transferred from the battery by the electrical current. State the energy stored in the battery. The energy stored in battery is chemical energy. This is a question from chapter 2. Make sure you are familiar with all the energy sources and the transfers of energy. Next, part 4. Calculate the total resistance of the circuit. Since this is a parallel circuit, this is the formula to calculate it. We've got two resistors of 90 ohm and 70 ohm. Just put this in your calculator and you will get 8/315. But this is not our final answer because this is the value of 1 over R total. So to get the R total, we're just going to inverse this, giving us 315 over 8. In two significant figures, the final answer would be 39 ohms. Alright guys, that's all for the revision from Chapter 4, Electricity and Magnetism. For the next video, I'll be discussing on another topic. Please let me know in the comments which chapter I should go through with you guys. Bye, have a good day.